As you can see from the image here, my talk is going to have something to do with paradoxical dice. It's sort of an extension or intensification of the idea of non-transitive dice, a well-known topic here. My co-authors are Ron Graham and Al Hales. Here's Al doing something he likes to do. Here's something the other two authors like to do. And here's Ron taking an exercise break during one of his talks, and I'm delighted I don't have to take that particular kind of exercise break. I thought I would at least, before delving into non-transitive dice, do a quick little bit on why some of these paradoxical effects can, or how they can arise in real life in sometimes consequential ways. Suppose you're a dean of sciences at some university, and the president wants to ask you the ticklish question of how well you're doing on hiring women. So you go to each science department and find that you have a higher fraction of women than in every other science department in your athletic league. The president says, well, fine, but if we look at your division together, collectively, you have fewer women than all of the other science departments in the Big Ten. You say, what? How can that be? And is that even possible? And of course, I wouldn't ask you the question unless the answer was yes, but nonetheless, this presents some issues. Okay, non-transitive dice. My favorite example, and I think the idea of non-transitive dice at least go back 65 years to Poland. But this example, I think, was one Martin Gardner liked. Take the rows of maybe the simplest 3x3 magic square, 2, 6, 7, 1, 5, 9, 3, 4, 8. Think of those as dice. I'm a mathematician, so I don't think of physical dice. I think of dice as a set of integers that represent equally likely outcomes of some random event. And of course, you're not surprised to find out that A is better than B. What do I mean by that? I mean, if you compare the outcomes of rolling those two dice, Alice has a higher outcome, larger outcome than Bob in 5 of those 9 cases. The probability that A is higher than B is 5/9, and Bob has a better die than Charlie, and whoops, Charlie has a better die than Alice. So we're not terribly surprised by that here, but here is the issue. I'm now going to try to intensify that effect by letting each of the players roll their dice twice. So A squared, I'm going to write it, is the set of outcomes that you get by rolling A twice and then adding. And yes, if you're fussy, that's not a set, it's a multi-set. All the outcomes are equally likely. And you'll find out that well, that didn't really intensify the effect very much. In fact, it's been reversed. I'll remind you that there was a cycle went in that direction when you rolled once, and if you roll twice, lo and behold, it goes the reverse direction. I think this phenomenon is 25 years old. And now let's roll 3 times and see what happens. Of course, I'll call that the cube of the dice, and it looks like it reverts until, lo and behold, Charlie is less than Alice. How can we sort of organize that idea? If you have n players and you want to record the outcome of a tournament, you take each edge between those vertices and put an arrow. I guess the way I've done it, the arrow is pointing from the winner to the loser. And with just the regular dice, we get the first tournament, alpha for alphabetical. If we sum twice, take the squares, we get the reverse tournament, beta for backwards alphabetical, I guess. And for 3 dice, it looks like the tournament is Alice wins. Okay, so those are 3 tournaments. What happens is we start allowing higher and higher powers. One question to ask yourself is how many tournaments are possible? Well, the answer is 8. There's 3 choices you have to make. And lo and behold, here's the answer. For 1 and 4, the answer is alpha. For 2, 5, and 8, the answer is beta. For all other integers, Alice wins. Okay, now think of a larger number. I'm sure you're thinking of 5 because that's what my slides are prepared for. Okay, so now we're going to have 5 dice. What can we do? We want to maximize the strangeness of the dice. How many tournaments are there? 10 edges, 1,024, 1K worth of tournaments. Let's ask if we can have all of those. 5 dice are wild if, all of those tournaments occur when you take powers. And just to make this a little extra challenging, I'm going to require that, in fact, they not only occur, but there's no final winner. They all occur infinitely often. And the theorem is wild dice exist. I could stop here in my remaining 20-some seconds. I'm going to give you a really fast outline of a proof. First of all, a die is nice if not only are the sum of its values 0, but the sum of its cubes are 0. It's A mod M if all of its values are congruent to A mod M. And the lemma, this really is a lemma, although it's a little non-trivial. Given A and M, there is an A mod M die. That's nice. Here's an example, and I admit it's very misleadingly simple. -1, 1 is nice in 1 mod 2. And here's a theorem that I won't bother to read that tells you how to tell when one dice beats the all 0 dice. Why is that relevant? Well, if you want to compare 2, you subtract and then compare against all 0. And here's the first sentence of the proof. Take those dice and then just follow that, use that theorem I just had. And if you want more details, this appeared in the monthly in 2018. Thank you very much.